Broadly speaking, there are three main components to understanding climate change. There's knowing what's come before, and scientists have a variety of tools for tracking past climate, things like ice cores, ocean sediments, and tree rings. Then there's measuring what's currently happening. There we get into the realm of thermometers, carbon dioxide sensors, and of course satellites. Last but certainly not least, there's the need to predict how climate will change in the future, and that's where climate models come in. One of the most controversial aspects of climate models is the role of clouds. Dr. Larry Berg is a senior scientist in atmospheric chemistry and meteorology at the Pacific Northwest National Laboratory. He oversees the two-column Aerosol project, whose goal is to better pin down the effects of atmospheric particles and clouds on climate. Welcome.
Thank you.
There are many different types of climate models, of course. Some are trying to predict precipitation or other climate factors. The ones that your data is mostly feeding into, as I understand it, are these very broad models that are trying to really put an overview on what we call the Earth's energy budget. What do we mean by the energy budget? What goes into that?
Right. By the energy budget, we mean really the amount of energy that's received by the Earth and the Earth's climate system at the top of the atmosphere, how much energy is absorbed at the surface, and then how much energy is actually going out. The Earth system reflects some sunlight back out to space, but there's also long wave emissions, so emissions from clouds and various constituents in the atmosphere. To the first order, the atmosphere is in what we call radiation balance, that the amount of energy in is equal to the amount of energy out, and the temperature more or less stays constant. At least stays constant when averaged over 30 years or so. As we change the chemical composition of the atmosphere, as we change the number of particles, as we change the properties of the clouds, we could change that energy balance so that either more or less energy is actually exiting the climate system and could change the global temperature.
So the project that you run, the two-column Aerosol project, let's break that name down. And first of all, you already mentioned aerosols. We're not talking about like an aerosol spray can. What is an aerosol?
The dictionary definition of an aerosol is a particle in a fluid. And so we're looking at tiny little particles in the atmosphere. Those people on Cape Cod, you're well familiar with sea salt and salt spray and salt particles in the air. So it's particles like that. Some are naturally occurring. Some are man-made. Diesel exhaust has a lot of soot, so there's a lot of soot particles.
And then these particles are important in actually helping clouds to form?
Yes. In the atmosphere, the water doesn't spontaneously condense. It has to condense on a particle. And so the more particles, if we change the number of particles, you could have an impact on the cloud. So you increase the number of particles, you have more cloud drops. That can have an impact on the amount of sunlight that the cloud reflects. Smaller drops leads to more reflective clouds, more sunlight going back out to space. It also can change the cloud lifetime because you can delay the onset of precipitation. So rain or snow doesn't start falling from a cloud until the drops or snowflakes are sufficiently big that they fall out. And so if you start with smaller drops, it's going to take you longer to get to the point where they start falling.
So, but the aerosol particles themselves can also have an impact on climate, not just through forming clouds, but through reflecting light and energy themselves.
Right, that's absolutely correct. There's particles that we like to refer to as white particles that tend to scatter light, and there's black particles like soot, that tend to absorb sunlight. And so if you are absorbing sunlight, then you're reducing the amount of energy that's reflected back out to space, and you're absorbing more energy into the climate system. If you have bright aerosol, then that reflects more light, and so it actually could have a cooling effect on the planet. And really, to get an idea of what I mean by white and black aerosols, if you think about a hot, humid day and the sky turns a milky white, that's because the water vapor is condensing on the particles. The particles are getting bigger and scattering more light. There's a lot of uncertainty, though, in exactly the nature of these black carbon particles than you might anticipate.
I mean, this is really fascinating. We're talking about trying to figure out how climate, this enormous global system, functions, and yet to understand that, we have to understand these microscopic, small little chemical and physical processes, and somehow try to span those two scales. It's really quite incredible.
Right. That's one of the things I think makes meteorology and climate science so intriguing, is that you do have to think across all these scales and different processes. But it's also what makes it very challenging, because you have to consider a wide range of spatial scales and a wide range of time scales.
Very interesting. Now, the other aspect of this project, the two-column aerosol project, is, of course, the two columns. So what are the two columns?
The idea of the two columns is really to investigate the aerosol and cloud properties in two columns, one relatively close to North America and one further out to sea. We selected Cape Cod so that we could be really downwind of some major pollution sources, and look at what happens to the air as it advects or travels out off the continent.
So what are those pollution sources? Are we talking Great Lakes power plants?
It could be power plants. It could be just urban emissions associated with automobile traffic. Not any one particular source. Just the general emissions coming off of New York City, Boston, the whole Northeast. The study we're conducting has a number of interesting aspects and unique aspects. One is just the idea of doing the two columns, where we have two columns that we sampled the same two columns with some regularity. So we have surface instrumentation at the bottom of the first column, which is on Cape Cod. And we also are able to do measurements with aircraft. So this past summer, we had two research aircraft, what we call an in situ aircraft. So that's aircraft that actually is measuring within the aerosol layers. And it has a wide range of instrumentation to look at particle size distributions, particle chemical composition, atmospheric states, so things like temperature, humidity, and winds. And then we had a much higher aircraft that had a downward-looking LiDAR. And a LiDAR is similar to a radar, except that it uses lasers. And, of course, it's eye-safe and all that, so there's no danger to anyone. But the particles in the atmosphere reflect that laser light back to their sensor, and they're able to infer the structure of the aerosol. The second column is about 200 kilometers off, further out over the ocean. And that's one that we can only reach with aircraft. So we designed the study to have two what we call intensive operations periods, one this past July to look at conditions in the summer, and then one here in February to look at conditions in the winter, because we know that there's differences both in emissions and in atmospheric processes between the two seasons.
So the differences in emissions, is that just that people are doing different activities and that causes different emissions, or do we have a sense of what causes those seasonal differences?
There's two primary differences. One is the energy use for heating, and the other is really looking at emissions from plants, because surprisingly, plants can emit various chemicals, and those chemicals can react in the atmosphere and form particles. And so we tend to have more of those particles in the summertime. In the wintertime, when the plants are largely dormant, it's not a factor.
You've got a fair bit of data so far, I'm assuming. What have you learned so far? Are there any conclusions you can draw yet?
Well, it's a little bit early to be drawing conclusions because it takes us a while to digest the data. We've pretty much now just getting our hands on the summertime data. So it actually takes a lot longer to analyze the data than to collect the data. But we're certainly getting a high quality data set that we can use to evaluate models. The two-column aerosol project is an example where we're really trying to specifically address the uncertainties in the climate models to help us get better estimates to the future.
Do you expect anything that comes out of this project in terms of refining the climate models to change the big picture in any way?
I don't know that it will change the big picture. I think it could reduce the uncertainty in what the big picture will be. And that's really what we're trying to do, is gather the data to help the representation of these various phenomena in the climate models so that we can get as good an estimate as we can.